All right, looks like we got most folks in and seated, so we'll get started. My name is Ryan Woolley. I'm with the NANOG Program Committee, and I'd like to introduce Ron Monica from Juniper Networks, who's going to have a total for you on segment routing.
Hello, my name is Ron Bonica, and before I start, I'd like to ask the group a question. How many of you today have MPLS enabled in your networks? How many starting to experiment with SR? Okay, there's a good number of people, so that means I better get the details right. Before I start, I have a small confession to make. SR has two names. Segment routing is the one you all know. In the IETF, SR was standardized in the Spring working group. Spring's a kind of awkward backronym for source packet routing and networking. And somehow they got Spring out of that. Well, in any event, some vendors call it SR, some vendors call it Spring. It's the same thing, it's interoperable. My employer calls it Spring. So when you see the marketing guys at the Beer and Gear, tell them Ron talked about Spring. You know, boing, springs. Okay. Now, let's leap into the talk. First, what is SR? And it's a couple things. One is it's a tunneling technology. It encapsulates a packet in something else and it ships it across the network. And that's kind of boring. We all have a million tunneling technologies. The interesting part is that it's a traffic engineering technology. A router can use SR to steer a packet along a path other than the IGP least cost path. So it makes it pretty much in the same ballpark as RSVPTE. And it may be more. People are finding new and interesting applications for SR, like SFC, service function chaining. So let's dive into what SR is and what it does for a while. First, we need some terminology. We need some words so we can all play the same game. An SR domain is a collection of SR-capable routers. And in that domain, routers play ingress, transit, and egress roles, just like any other MPLS network. Also, inside that domain, you can mix in a few non-SR-capable routers. And we'll talk about ways that we can do that. Next term we need is an SR path. An SR path connects the ingress to the egress. It can be different than the least cost path, that's why it's traffic engineering. And the path contains segments. Segments are what makes this different. A segment connects 2 points within the SR domain. It can traverse one or more hops, and it's represented by a segment identifier, or a SID. A SID identifies a subpath, and it can either have node local significance or domain-wide significance. Now, I'm sure that bullet means almost nothing to you now. It'll mean a lot by the end of the presentation. But before we go anyplace, let's have a nice picture so that we can tell what all these terms really mean. Here we have an SR domain. It's a bunch of routers. We have an SR path connecting an ingress and an egress. The path contains 3 segments, A, B, and C. A is a 2-hop segment, B is a 1-hop, C is a 2-hop. So we've all got our terminology. Now we can start to play the game. Let's talk a little bit about traffic engineering with segment routing. And let's talk about how traffic engineering has been done in the past. There are 2 traditional approaches. One approach is to encode all of the path information in the packet. How many of you remember the IPv4 strict source routing option? Raise your hand if you remember what it is. Okay, that's an example where you encode the whole thing in the packet. The strict source routing option has in it every node that you're going to visit, and you will visit no node but that. And if you use this option, the only thing you need as far as routes in your network is direct routes. You don't need any static routes, you don't need any IGP, you don't need anything. That's one approach, which incidentally nobody uses. Another approach is to store all of your information in the network. So your path is represented by a single token. The network has all the path forwarding state in it that it needs, and that token just gets swapped along the way. This is what RSVP signaled MPLS does. So those are the two traditional approaches. At one extreme, we put all of the information in the packet. At the other extreme, we put all of the information in the network. Now, if we have two extremes, we must have something in the middle. And let's talk about that something in the middle. In this hybrid approach, we divide the path into segments. Sound familiar? We just saw a picture of that, a path divided into segments. The packet header lists all of the segments, but not every node. It just lists the segment endpoints. The network has enough state in it to get you from the ingress of a segment to the egress of a segment, but the packet has what's needed to get you from segment to segment. And some examples of this, anybody remember the IPv4 loose source routing? In that case, it had a list of nodes that you had to visit. There could be other nodes in between them, and to get to them, you needed some kind of routing in the network. So in this hybrid approach, you need enough state in the network to get you from segment endpoint to segment endpoint, but the packet has in it a list of segments that you must visit. By the way, segment routing uses this hybrid approach. Let's talk about what segment routing does. It defines multiple segment types. Some of them traverse only one hop, some traverse multiple. And it enumerates the segment types in the path, but not necessarily every node in the segment. The network has enough information in it to get you through a multi-hop segment. So far, is everybody with me? Okay, these have been abstractions at 30,000 feet. Now let's come down to 20,000 feet. In segment routing, we have lots and lots of segment types. For the most part, most of the people who are deploying segment routing are using, well, the prefix is used by far the most, but they're using these four. There are four types we're going to talk about today. Two we're going to really spend a lot of time on, adjacency and a prefix segment. An adjacency segment contains exactly one hop, and it represents an IGP adjacency. It represents a link. A prefix segment represents the IGP least cost path to a prefix. Now that least cost path may traverse many nodes, it may traverse one node, but it's the IGP least cost path to a prefix. Anycast is very much like a prefix segment. The only difference is that prefix is advertised from many points in the network. So it's the IGP path to the closest instance, to the IGP least cost instance of that prefix. And then finally, there is the binding binding segment. The binding segment represents another tunnel, maybe an SR signal tunnel, maybe an RSVP signal tunnel, maybe some other kind of tunnel. You can think of it as being a shorthand. It's a way to put a tunnel in a tunnel. So, in this presentation, we're going to spend most of our time talking about adjacency and prefix tunnels. If we can wrap our heads around that, we can declare success. We'll talk a little bit about Anycast and binding, just because you need them for some purposes. So, remember we said that SR was an encapsulation mechanism? Well, SR, it's a traffic engineering mechanism that relies on an SR-capable encapsulation. And right now there are two SR-capable encapsulations. One of them is MPLS, the other is IPv6. Let's talk about the MPLS encapsulation first. In the MPLS encapsulation, the SR path is represented by an MPLS label stack. And each entry in the label stack represents a segment in the SR path. Now, this is a strategy that you've seen before. Let's see, I remember I've seen a few hands going up when we talked about loose source routing. You know, raise your hand if you remember loose source routing in IPv4. Okay, in IPv4, the option has a bunch of IP addresses in it. Each IPv address really represents the end of a segment that you must visit. Well, in MPLS, we do exactly the same thing. The ingress router imposes a label stack. Each label gets you to the endpoint of a segment. And the network has enough information in it to get you from each segment ingress to each segment egress. Now, in IPv6, it's slightly different. Again, we need an encapsulation mechanism, and the encapsulation has to enumerate all of the segment identifiers. So what we do in IPv6 is we wrap the packet in another IPv6 header, and the IPv6 header has an IPv6 routing extension header in it, a special one called the segment routing extension header. Like any other routing extension header, it has a list of addresses in it, and those addresses are actually SIDs, they're segment identifiers. So just like IPv4 lists the IP addresses you need to list, SR with MPLS encapsulation, each label stack entry represents a segment identifier, and IPv6 and the SRH, each entry represents a segment identifier. And if that didn't stick in your head, don't worry about it. We're going to give you examples. So let's talk a little bit about this MPLS encapsulation for a little while. And let's talk about labels. Some labels have local significance only. And that's a very good thing. Well, some SIDs have local significance only. And that's a very good thing because MPLS labels have local significance only. So you can map the SID directly to an MPLS label. SID1 equals label 1. There's no need to coordinate SIDs throughout the domain. So in the next slide, we'll talk a little bit about how this might work. Here, we're going to build an SR path from R1 to R4. So it's going to have to visit R2, 3, 7, 6, 5, and 4 in that order. Now, to make this work, what's going to happen, let's take a look at it for a minute at R2. Oh, by the way, we're building this from all adjacency segments. So one segment is R1 to R2, another is R2 to 3, another is 3 to 7, 7 to 6, 6 to 5, 5 to 4. So let's take a look at what R2 does. We take a look, let's see if you can see my pointer there. Can you see my pointer? Yes, you can. We take a look at what R2 advertises into the IGP. It advertises that it has local label 81 representing the link to R1, local label 82 representing the link to R3, and local label 83 representing the link to R5. If you take a look at all of these green boxes, whoops, I lost my pointer. If you take a look at all of these boxes, they're all advertising a SID and associating it with every link they have. So R1, the ingress router, knows everybody's SIDs. He knows that the first thing he wants to push on the label stack is that he wants the packet to visit this link. So the first thing he will push on the stack is the 82 advertised by this guy. The next thing he'll push on the stack is another 82 advertised by this guy. And finally this 82 and this 82. So when R1 builds the label stack, he pushes all those labels representing each link, and then he forwards the packet to R2. R2 pops the outermost label and sees an 83 and forwards it to R3 because 83 represents the link to R3. R3 sees the exposed 82, pushes it to R7, and so on. So we pop a label off the stack at each hop along the way. Now, the first thing is, could everybody see my pointer as I was pointing along there? Okay, it showed up on the screen well enough. Does everybody get the idea here? In this case, how much state is maintained in the network? And it's a question for the audience. Where is all the state?
As many as neighbors of the single router.
Well, the single router puts the state in the packet. The state is actually the state that you need to get the packet from R1 to R7. R1 knew it, and R1 put it in the packet. This is the packet header you're looking at. When R2 got it, it had enough of the packet header left to route it the rest of the way. R2 pops off some and sends it on to R3. So the state, in this case, R1 knew it, he put it in the packet, and the packet carried it with him as it went to the egress. Now, in this case, we have a good example of a local label. Why is this a good example? Let me ask the audience. Who can venture a guess? Why are the labels local here? Exactly. 82 and 83 are the only two that ever got used. And everybody and his brother advertised 82. Okay, this is the easiest case to understand all adjacency labels. It's also a very rarely used case. The reason it's rarely used, well, the first problem is your label stack can get pretty big. There are MTU implications. There are also implications if you're using ASIC-based forwarders, how many labels can he push? There's also an issue. What would happen if a packet were in flight and R3 were to go down? We'd have to figure out some way to do, either signal back to the ingress and send the packet again. We'd have to do something about restoration that's as yet undefined. So let's talk about a more common use of SR. Adjacency labels are used sometimes, just not as commonly as prefix labels. Let's talk a little bit about prefix labels first. Prefix labels have local significance. Let's say a router has a prefix behind it. He says, I'm going to advertise my accessibility to this prefix. I'm going to associate it to label 5. Nobody else should use label 5 for anything else. This label has domain-wide significance. It has to be assigned very much as we assign private IP addresses today. They have domain-wide significance. You keep some little registry in your domain, so you're sure not to advertise the same, two prefixes with the same domain. Each node, now here's the problem. We need to map segment identifiers to labels. Each node is going to reserve a block of labels. And this block of labels is to be mapped to global segment identifiers. Now, every router can potentially reserve a different range. This vendor might reserve 1,000 through 2,000. That vendor might reserve 5,000 through 6,000 or 5,000 through 7,000. So they call this range the segment routing global block. And the label is actually, the SID is actually an offset into that block. That's how you calculate the labels. And we'll see that in an example in a second. Okay, here's a good example. R7 has a prefix that it wants to make accessible through segment routing. So it advertises something. It advertises that it has prefix 7. Its sRGB starts at 100, and that's it. Everybody, R1 through R3, R4 through R6, everybody who's not R7 needs an SR path to get there. So let's take a look for a minute at what R1 does to build his SR path to R7. In this case, everybody begins their sRGB at 100. So R1 needs to define a label that will get him to R7. He adds his sRGB to the number 7, what R7 advertised, and he gets label 107. And he pushes it to label 2. Notice he only had to push one label on the stack. He didn't have to push a whole bunch of them because R7 maps to the IGP shortest path to R7. R2 gets the packet. He says, oh, my sRGB starts with 100, so this must be SID7. SID7, how do I get it to R3 or to R7? Well, through R3. And by the way, I can do penultimate hop popping in this case. So he pops the label all together, sends it to R3. R3 forwards it there to R7. Now, let's go back to our initial question here. How much state is stored in the network? Which routers have state that's needed to forward this packet? How did they know which way? How did R2 know which way to send the packet to get to R7? Bingo, who said it? Okay, I buy you a beer after. That's to encourage people to answer the questions. You get a beer. Now everybody's going to leap up. Okay. Okay, so this is an easy scenario. By the way, you could replace LDP with SR. This is an example how LDP would work for SR, and you could do it that way. There are some reasons why you might not want to leap up to do it immediately. For instance, you might have your LDP deployed already, and there's no good reason to do it. You might like the bypass LSPs in LDP, but this is a simple implementation of LDP using just SR. So let's talk about a more complex implementation of SR. Here we want to get a packet from R1 to R4, and we want to take the scenic route through R7. You'll see something else is a little different in here. So we're taking the scenic route through R7. So what's the first thing that you see in the packet as it leaves R1? This SR path has how many segments in it? 2. How many labels on the label stack when it leaves R1? Why? Right, and every member of the label stack represents a segment in the path. Okay, that explains why there are 2. There's also something a little interesting. Take a look at the sRG bases. Everybody is announcing 100 as their sRGB base, except for who? R5. R5 advertises 200, so you're going to see a little jitteriness around R5. Okay, so let's talk about R1. It's going to push 2 labels on the label stack. The innermost one is the one that gets him from 7 to 4. How does he calculate that 104? Well, who advertised SID4? R4. Now, what label maps to R4? He's going to be 100 because that's his sRGB base. Now, the innermost label, R7, who advertised SID7? Exactly. Now, let's take a look at the little jitteriness. The packet that arrives at R5, if you see the packet, it travels with 2 members on the stack from 1 to 2, 2 members on the stack from 2 to 3, 3 pops 1. So 7 starts processing label 107. He sends it to 6, and 6 swaps that 104 to 204. Why does he do that? Bingo! sRGB base at 200. 1 beer there, 2 beers? Okay. And there was 1 back there too, so I'm like a 6-pack down now. This has been a good crew. Okay. Let's talk a little bit about OAM. Does OAM work in segment routing? Yeah, if you're using the OAM that was defined for MPLS TP, that should work. Does MPLS self-ping work? Yes, it does, but you have to do some funny things. You have to put the ping in the nil mode. And trace will work so long, well, actually, depending on implementation, trace will or won't work. It works only if you copy the TTL from the outer packet to the inner, then copy it up and down the stack as you pop off stack entries, and then copy it again when you pop the last one. It won't work otherwise. And MPLS aware traceroute, same story. The thing where in the traceroute you see all the labels, that'll work only if you manipulate the TTLs correctly. Any questions so far? Everybody following so far? Give me a thumbs up if you're following. Thumbs down if you've fallen asleep, or a loud snore. Okay. OAM? Okay, OAM is Operations, Administration, and Management, and it's a way to figure out if a path or a link or in anything is healthy. Your classic OAMs in IP, ping and traceroute. Okay, now, we talked about how this works in a world of IPv6, in a world of MPLS. Well, there's another encapsulation, IPv6. And let's talk about how that works for a minute. Well, it has a canonical mode. And in the canonical mode, there are 2 ways it can work. First is the packet, sorry about that. The packet that originates the node, originates the packet is also the SR ingress. So it just puts a routing extension header in the packet. It includes it when it formats it in the first place. Another possibility is that the packet originates on your laptop. It's not it's not SR aware. It goes a few hops and it hits an SR ingress router. The SR ingress router encapsulates that packet in an IPv6 packet that has a segment routing extension header. Those are the 2 canonical modes. Then there's also a non-canonical mode. That's where the packet originates on a node that isn't SR aware. It hits an SR ingress, and the SR ingress inserts an SRH between the IPv6 header and the IPv6 payload. There's some controversy around that in the IETF right now, so I call that non-canonical, and we're not going to talk much about it. We're going to talk about the canonical mode. Oh yeah, and you can also encapsulate v6 and MPLS. So, what's encapsulated has nothing to do with the encapsulation. In fact, you could even encapsulate something that's not IP, like PWE header or something like that. So let's take an example of a packet going from, well, let's see, I didn't put labels on them, so let's use my pointer again. Going from this node to this node. It leaves its origination point with a very innocent source and destination address. We'll call them 1 and 5 since that's it. It hits an ingress node, and notice it got much longer. The packet length extended because we added an IPv6 packet and a segment routing extension header. The next header is no longer TCP. It's now segment routing extension header. The source address is this node, the ingress, the SR ingress. And the destination isn't the SR egress, it's the end of the segment that we're on at the moment. Now, take a look down here at the segment list. The segment list has on it number 3. Notice we're on 4, we're the ingress. Number 3 is the next one we have to visit. And the destination is number 3. Now this is the egress. I can see you're looking confused. This is how routing extension headers work in IPv6, even before segment routing. So we've inserted all this stuff. We hit this node. We don't change anything. The node that we're on right now isn't even SR aware. It knows it has a route to 4, and it's going to forward the packet to 4 without looking at the segment routing extension header. 4 gets the packet, and he changes things. He says, I'm the endpoint of the first segment in this SR path, so I'm going to change the segments left to 0. Now I'm trying to get to number 4. I'm going to change the destination address, and I'm going to ship it off. He ships it. This node isn't SR aware. He just forwards the packet to the destination, which happens to be the SR egress. The SR egress gets it. He strips off everything, and the packet is back to looking exactly the way it did before it entered the SR domain. I see you're looking confused, so let's go back to this. Remember, we said that in SR, someplace in the encapsulation, you had to have a list of all the segments in the SR path. This is that list. And what we did was visited each node, and we updated the outer encapsulation to make us get there. Okay. Next slide. Okay. We talked about adjacency SIDs till we were blue in the face. We talked about prefix SIDs till we're blue in the face. Let's talk about some of these less common ones, which are actually becoming more common. Let's talk for a minute about the Anycast SID. It's the same as a prefix SID, but you advertise it from many places in the network. The reason you might do that is to give yourself some fast reroute capabilities. Let's talk about what happens if you're sending a packet, it's in flight, and the endpoint of your segment just goes away. The router reboots. How do you get the packet to its destination? Do you have to drop the packet and wait for head-end signaling to work and find a whole new path? Well, maybe not. If you've advertised the prefix from multiple places, especially on an ECMP, when one goes away, the other is still there. Take a look at the illustration here, and you'll see an example. The nodes in the middle, if one of them goes away, the others are still there. And especially if it's an ECMP situation, you're in much better shape. Now, yes, please. Yes.
Can you repeat the question?
Oh, yes, the question is you'd advertise the segments in the middle of the path as Anycast. And actually, the destination could be Anycast also. There's no reason why. Yeah, there's no reason it couldn't be. It would be an alternate egress for that prefix, and it would happen often. Let's say for a minute you had a site that was dual homed to 2 egress LSRs? Well, you'd advertise the prefix as an anycast from there. Okay. So let's talk a little bit about binding SIDs. Let's say for a minute, let's talk about an adjacency SID and talk about a binding SID as being a special case of that. In an adjacency SID, it's advertised by the head end, and it's telling you, if you want to use this interface, come to me with this label. Well, let's say a node, rather than having an interface to a partner, has a tunnel to a partner. Let's say it has an RSVP signaled LSP, or let's say it has a spring signaled LSP to get there. Well, one thing you could do is advertise a binding SID. One label maps to that. And when the router receives that binding SID, it does whatever it has to do to encapsulate the packet to get it on that path. Now, let's talk about a really good use case for this. Let's say for a minute you have a traffic engineered path that has 5 hops in it.
10.
10. I like it even better. And let's also say that you build one segment that brings you along the first 5 hops. Let's make it even more complicated. It has 10 hops, all of which have to be adjacency hops. You're not allowed to do it any other way. And I realize it's kind of a contorted thing to do. Well, what you might do is build an SR path from 5 to 10. Have 5 advertise a label, advertise a binding path to get there. Then 1, when it pushes its stack, pushes 1, 2, 3, 4, the binding label. So it goes to 1, pops 1, goes to 2, pops 1, goes to 3, pops 1, gets to 4, which brings you to the binding label, and then that makes it push 1, 2, 6, 7, 8, 9, 10. That way, at no point do you have all 10 label stack entries on the stack at once. Why would this be an issue? Why would you be concerned about how deep, obviously the binding SID is giving you a shorthand. It's giving you a way to represent n SIDs with a single label. Why is this important to you?
Pushing labels with A6.
Bingo.
And MTU.
Those are the two right at, oh man, I'm up to a 6-pack now. No, I'm beyond the 6-pack, I'm up to 8 beers. But those are the two problems. One is some A6 can only push so many SIDs, so many MPLS labels. Some more than others, but everybody's got a limit. The other is you really don't want the MTU growing too big, especially if you're bringing traffic to many, let's say, no, that won't break PMTU discovery.
Support fragmentation, so with MPLS you are done, you have to drop.
That's true, yes.
IPv6 later.
Mm-hmm. Well, let's think about what PMTU discovery is going to do. Sooner or later, PMTU discovery is going to kick in. You're going to send things back. But you don't want it to get too terribly large. Okay. So we've talked a little bit about segment routing forwarding, quite a lot. In fact, that's all we've talked about. We've talked about what a packet looks like as it's forwarded around through a segment routing MPLS forwarding plane, or as it's sent through an IPv6 forwarding plane. We haven't talked about the control plane one iota. So, a question for the audience. What things do we have to do? What are the requirements for the SR control plane? Well, one thing we saw is that it had to calculate the path. The ingress router had to decide what labels to push. What segments do I need to visit? The second thing is each node had to advertise its own sRGB base and the segments that it either originates or terminates. If you're terminating a prefix segment, you need to advertise that. If you're originating a adjacency segment or a binding segment, you need to originate that. So you need two things. You need an IGP and you need a path computation module. So let's talk about these a little bit. And let's start by talking about path computation. You can perform path computation in two places. You can either do it on a central controller or you can do it on the ingress LSR. Now, some path computations are really, really trivial. Remember the second example I put on the board where there was a single label 7 and from every place it brings you to 7? Well, that path computation is really, really easy. All you have to do is figure out what your IGP shortest path to R7 was, and for the shortest path, figure out what the sRGB base of the other guy is, and push that single label. That's really a trivial path computation. Another trivial path computation is where you statically configure it. I know perfectly well that there are 7 adjacency segments that I want to go through. I'm going to configure them statically, and that's really trivial. Both of these can be done either in a distributed way on the ingress LSRs or in a centralized controller. And you know what? If that was the extent of your problem, you probably wouldn't be using SR at all. You'd probably be using GRE tunnels. The odds are you're using SR because you have a TE issue. So let's talk about this non-trivial case where what you're doing is constraint-based shortest path first forwarding. Okay, in CSPF, by the way, are any of you running RSVP today? Okay, for all you people, this will sound really familiar because you've been here already. The first thing you do is you assign attributes to a link. You know, color, bandwidth, shared risk link groups. The next thing you do is assign requirements to a path. Say this path has to go from here to there, it can only traverse blue links, and it's going to reserve 100 megabits of bandwidth. Then you calculate the IGP shortest path from ingress to egress using only the links that satisfy the requirement. So let's say your requirement was to traverse blue links only. You prune every link that isn't blue out of your link state database. You find the IGP shortest path, and that's it. And you've calculated it. Then you find the segments that go there. And you know, as I just said before, the piece of information you need to do your CSPF is the LSDB and another database that I don't mention in the slides called the TED. The LSDB and the TED are cousins. The IGP floods link state information throughout the IGP domain so that every router in the IGP domain has an identical copy of the LSDB and the TED. The LSDB tells you about network topology and what SIDs originate or terminate where. The TED tells you about link attributes. So anyhow, CSPF is almost exactly the same as it is in RSVP-TE, and it relies on the LSDB and the TED the way it did in RSVP-TE. The next thing you need to do is create fib entries. When you get a label, well, let's see, might as well read the slide. On each node for each global SID, you create a fib entry that swaps an inbound label for an outbound label as required by the sRGB downstream and puts you on the IGP shortest path. For each node on a local SID, you have a fib entry that does a pop and forwards. And again, you can create all of the fib entries you need from information that's in the LSDB. Well, hey, let's think about this for a minute. Everything we need is in the LSDB. And here's the breakthrough. Segment routing loves IGPs. Everything you need to do your CSPF is in the IGP. Everything you need to create your fib entries is in the IGP. ISIS and OSPF have both been enhanced to flood all this information. So SR requires an IGP and little else. It requires an IGP and a path computation module, be it distributed on the ingresses or on the central controller. But you don't need an LDP, you don't need an RSVP anymore. Now, let's talk a little bit about convergence after a failure. First, let's say that you have a prefix segment, and the prefix segment has 5 hops in it. And a node goes down in the middle of that prefix segment. How do you restore? Question for the audience. How do you think restoration is going to work?
Fine.
Right, the IGP reconverges, and the packet is still fine. It still has all the right paths it needs to visit. It's just that the path between the route between the beginning of one path and the end of that path has changed. So you are as fast as IGP convergence is going to work. That might not be fast enough for you. So what are some things you can do to speed this up? Okay, TILFA is the one that's I'm looking for. In TILFA, you have backup routes to get you around failures. So you don't have to signal all the way back to the head end. Packets that are in flight might make it. Another situation that you have to worry about is what happens if the failure happens at a segment endpoint. And let's take a look. Let's go back and find an example of this. Way back. Let's take a look at this example. What happens if R7 reboots and a packet is in flight?
Discard. Because
Discard. There's nothing you can do because
it has
the state is in the packet. The packet says it's got to visit R7, and R7 ain't there. So there are 2 possible solutions. One solution is you discard the packet. There's some out-of-band OAM mechanism that, let's get back to the slide, that tells the path computation module that this segment is now not in it, and it starts building subsequent packets with a different label stack. Fast reroute consideration possibilities are under consideration, but right now, head-end signaling is the way to fix this kind of failure. One way you can mitigate the effect of this is use the Anycast SIDs, the way we talked about a few slides back. So that way, yeah, the end of the segment is gone, but there's another one just like it waiting to take over. So let's talk a little bit about the controller. We kept hinting at the fact that there are two options for this controller. One option is to centralize it, and the other is to distribute it. In one situation, it must be centralized. For those of you who are using RSVP today, how many of you have bandwidth reservation in the constraints? How many are using RSVP to reserve bandwidth? Okay, when you do that, what's going on is RSVP sends this path message downstream, and when an intermediate router gets this, it reserves the bandwidth and advertises that reservation into the IGP. So everybody in their link state database knows how much bandwidth has been reserved on each node. In SR, there is no path message. An individual router has no idea how much bandwidth has been reserved on it. Before, he could look into his LSDB to get a global view of bandwidth reservations. Now he can't. So, who has that global view? How do you, when a path computation element is figuring out how much bandwidth is on a link has available, where does he get his global view? Well, he only has one possibility, and that's if you centralize path computation in a controller, he has the global view because he made all the assignments. So if you're using SR to reserve bandwidth, then you must go with a centralized controller. Now, going with a centralized controller is a good thing. The reason it's a good thing is because now, not only do you have a centralized view of bandwidth allocations, you have a centralized view of everything. Let's say for a minute you're collecting analytics from all your nodes. How much traffic is going through this node? Do I have diurnal patterns of the traffic, coming and going? Do I have weekly patterns? Well, now that you have all this stuff in one global place, maybe you can use that global place to do more intelligent path computation than you would have done had you had path computation distributed among all your ingress LSRs. So, it's true that you have to centralize to do bandwidth allocations, but bandwidth allocation may actually be a very good thing. Now, there's also some risks associated with centralizing anything. You now have a single point of failure and congestion. You have a single performance bottleneck. And you can mitigate this risk if you do redundant controllers. Again, it's going to require a little bit of synchronization, but it's probably worth the effort. Now, the controller somehow is going to need to get all of the information in the LSDB. Remember we said that you need LSDB information to compute paths? Well, it needs to get it somehow. How are you going to do that? One possibility is you let the controller participate in the IGP, let it be a passive member. Another is you use BGP link state to export the LSDB to the controller. Next thing you need is the controller needs to be able to send a list of segments down to the router. Two options to do that, PSAP and BGP. And finally, the controller is going to impose policy at the ingress router. What traffic to place on the SR path, and he has two ways to do that. Flow spec additions for PCP and BGP. So, what are the conclusions? Well, the big salient difference here between SR and its predecessors is that it moves state from the network to the packet. It simplifies the protocols. What used to be an RSVP now is a fairly simple thing. But it also raises some problems. We talked about OAM. We need this out-of-band OAM thing. Fast reroute, we need to rethink. We need operational experience. It's one of those things that it's promising. It's a good idea. We should work with it. Start deploying it in some controlled environments so we start to see how it works. Is it as mature as what you have in your networks today? Honestly, I can't tell you that. But it's worth some experimentation. It's worth some controlled deployment. And at this point, I'll open it to Q&A. I'll ask you some questions then to get it started. Anybody? Oh, here.
Hi, Tom Carter, Charter. I was wondering if you see any similar, or anything that would be a similar use case to a flow label in segment routing, or there's SR would do that automatically, or if there's a.
Okay, you're talking
something
about
else, same thing.
IPv6
Fat
flow labels?
Or like a fat label inside MPLS.
Okay.
Fat label, you mean for ECMP?
Yes.
Okay, so what you want to do is branch a path on two separate physical paths. Kind of like, we call it TE++.
Well, we call it in RSVP environment.
We call it TE++. Okay, I had to get the name straight first. To get the terminology straight, since I was confused with it, I'll make sure everybody else understands it.
No. The question was about fat label or entropy label things.
Okay, an entropy label, you certainly could push an entropy label on the stack in segment routing. The question is, where would you push it on the stack? If you push it at the very top, some ASICs may not be able to look that far. So maybe, rather than dealing with entropy labels in SR, a good thing to do would be to dance around the whole problem by defining links small enough that you'll never have to deal with entropy. Let's say for a minute you have an ECMP that goes 5 ways. Give a different SID to each one of them and treat them as an adjacency.
Okay.
So that way you never need to deal with it. Because there is a problem with entropy in SR. The problem is, where do you put the entropy label? If you put it at the very top of the stack, it might be so far up the stack that downstream ASICs can't see it, in which case your load balancing breaks.
Yes,
If you put it on the bottom of the stack, then you have to preserve it and move it. So the
exactly, that's what you have to,
Yeah.
like every other label is a.
Well, it wouldn't have to be every other label. You move it at every hop.
Yeah.
You need to pop in from the middle of the
Yeah.
stack and shift this up.
Yeah, exactly. Yeah, that's where I was trying to get at, see if there's something there.
Yeah.
And then I have another question of, how do you see SR working in a multi-AS BGP environment?
Okay. Typically, MPLS lives in only a single AS. If you think about the way RSVP works today, RSVP dips into the LSDB just like SR to do its path computation. When you need to go across ASs, there are a couple things you can do. One is you can use BGP to advertise labels, and you can still do that with SR. You can use BGP to advertise labels because they're just labels.
That's pretty easy.
That's,
Right?
yeah, that's,
The only question is if this BGP label, if in BGP you move the stack, and then in inter-AS you have 20 labels, 100 labels, God knows how much, which is kind of a problem. Or it could be equivalent to the path label, binding SID.
well, what you do is advertise a binding SID across the BGP domain.
Exactly.
So you'd allocate a binding SID and then advertise that with 3107 advertisements.
Okay,
But both good questions.
all right, thank you.
Any more?
What is the viability of using any other Simeon Mitov Berkeley Lab? What's the viability of using any other encapsulations like Ethernet or something like that?
Okay, using other encapsulations for, well, you could build more SR encapsulations other than IPv6 and MPLS in theory. What you would need is a place to put the list of segments. Now, given encapsulation foo, if it has a place to put a list of segments, yeah, you could do it. The next question is, why would you want to? And I'm putting the question right back to you.
Right, so I guess if you could do it with something like Ethernet, maybe you could do it with some cheap silicon. But I guess there you typically have like 2 labels. Is that useful?
Well, what it does is, there are two ways you could do it with Ethernet today. Encapsulate Ethernet and Ethernet to get two labels. Or if you have a deep path with many, many segments, yeah, it would make sense to do it. You know, I'm not going to say what makes economic sense. An Ethernet guy would know that. But theoretically, it's possible. Any other questions?
Hello, Joel Stetman, also with Juniper. I hope I'm not putting you on the spot. One of your first slides brought up having a segment routing domain with sections inside that are not segment routing aware.
Yes.
Can you give examples of how that works? Is that
Sure. In fact, let's go back to click, 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 click. This example. Here, the next node is not segment routing aware at all. It just forwarded an IPv6 packet and didn't look at the segment routing header at all.
Sorry, I meant expressly for MPLS. IPv6, I can see how that works based on the header manipulation that happens.
Okay, let's go back a little bit further. Let's take a look at this fellow. Let's say for a minute that R2 was not SR aware. If somehow you could stuff a route in R2 that says when you get a packet for 107, pop the label and forward it to R3, it would work. Now, there are many ways you could stuff that route in there. One is make it SR aware and make it compute the route like any other SR router. The other thing you could do is put a static route in there. Or you could have the controller stick it down there. Is it pretty? No. But theoretically possible. It's much easier and it's much more natural than the IPv6 example.
Thank you.
More questions?
Yeah, Jason here from Microsoft. Quick question. So can you talk more about controllers and kind of how you would distribute them, I guess, in case of failure scenarios and, you know, some other types of things like that?
To be totally honest with you, I'm not an expert on that. One thing you could do, is, you know, the most obvious is to have two of them and have every router in the network talk to both. But Rafael has a good idea because he talks.
Actually, our implementation, but now it's implementation specific. It's free. They're running as a cluster. Because we don't want to go to the situation of split brain, right? So with free, this which has the peer left, at least one peer, is the active one. But that's typical for that's implementation specifics. The bigger interesting question is how to have multiple controllers managing separate domains, right? If the scale requires us to go out, but I think there is no answer for that at the moment. Well, you have to remember that with the SR, this seed has to be continuously, the node seed, this has to be continuous and unique. So I don't think we are at the place when we talk about the thousands or tens of thousands of routers in single SR domain that we have to think about splitting controllers. We are not there yet.
And you had something before.
Actually, I was just commenting on the prior question. I was just thinking,
Could you come to the mic?
So I was just commenting on the prior question that if you could possibly use a binding set to put the packet on an RSVP tunnel or an LDP tunnel where the intermediate routers in the LDP tunnel don't necessarily need to be SR aware.
Oh, you're right. Didn't think about that answer, but you're right. Get to any other tunnel to get across the... And it just happens that in the IPv6 example, you're on one. but you could get on another one. Anyway, more questions? Well, with that, one more.
You mentioned something about service chaining. Could you maybe give some examples of using segments?
Okay. Right now, well, I'm going wildly off topic right now. Right now in service chaining, there's something called a NSH, a network service header. And that header defines the path, and there's enough state in the network to get you from service function to service function. That's the IETF blessed right way to do it. But if you were a revolutionary kind of character and you wanted to do such things, you could represent that service chain as a MPLS label stack and have each each service function pop a label and forward to the next one. But all in the area of exploration right now. Yes?
Hi, Wayne Tucker, Oracle. So it seems like we're moving complexity from one place to another and reintroducing a lot of problems like ECMP hashing and centralized state. So what are the real driving use cases for this? Like, what's the justification?
Okay, the first thing is, I'll remove the arrow from my side and say that your question is not only appropriate, but it's telling. We have a bag of problems that weighs 5 pounds to solve. And no matter where we put the solutions, we're going to need 5 pounds of solutions. We're moving the problem from one space to another. Now, I think there's some advantage of moving the problem from one space to another in some use cases. For instance, let's say you are in a situation where signaling LSP state just isn't working for you, either because there's a certain amount of it, or there's something about your network, or maybe you're in a green field where this solution is right for you. In those solutions, SR is right for you. I'm not going to stand here and tell you that SR is the right thing for everybody. If you've got an MPLS network and your signaling is working right now, and your state isn't knocking you over, there's no benefit to move. We actually need more experimentation to find the use case where segment routing is the right thing for you, or RSVP is the right thing for you. I guess in the last 2 minutes, I'm allowed to make a brutally vendor-specific statement. We're equally invested in both, because RSVP-TE is the right thing for some people, SR is the right thing for other people in different environments with different kind of hardware in their network and different kinds of use cases. And we really need more operational experience to discover when SR is the right thing and when RSVP is the right thing. But until that day, we're going to support both wholeheartedly. Anyhow, end of vendor rant. And I apologize for the vendor rant. I'll buy everybody a beer. No, I won't buy everybody a beer. I can't afford that. Any more questions? And I see that I would get the hook in 6 minutes, so I guess we're done. Thank you all very much. It's been great. Thank you.
So your next step.